I decided to investigate what happens if we do a higher resolution, 5 km. To provide some context, 15 km with a bit of GIS analysis, roughly estimating. It's about, let's say we stand in Georgetown, that's about up to Grove on the east bank or up to Lusignan on the east coast, which represents the image to the top left here. In the center of both images, you'll see a gray dot. Now, what the WRF gives you is one value in the center there that represents what is likely to occur or the forecast for that entire region. So imagine getting one rainfall or one temperature value for an area this big. Now we know it's natural and common, not just in Guyana, for rain to be falling in one village and then one village down, there's no rain. Or two villages down, there's no rain. So imagine when we have a difference of 5, 6, maybe even 7 villages. Quite large. And so what I would have investigated is a 5 km resolution. And we could see at the bottom here, that's about, again, standing in Georgetown, up to Agricola on the east bank or Ogle on the east coast. Still a relatively large area, but one would argue that is much more reasonable. Now, I would have wanted, and I do want, to get to a higher resolution in the future, maybe 2 km or 1 km, but due to my resource constraints right now, the demand to run this model, 5 km is the best I can do at the moment. But even with this 5 km, I want to show you some improvements. Now, this is just a rough example. On the event from 2016, we could see with 1 km to the top, and we're focusing on the crop here at the left, how much of a difference it makes when it is changed to a 5 km grid, how much more detail is picked up, right? 1/3 of 3.9, and we could see the 5 km grid was able to pick that up a lot clearer than the 15 km grid. Let's look at two of the better performing parameterization schemes, B and F, compared to the current one. The event from 2015. The current one did not so bad. B, in this case with the 5 km grid, it went down a bit in performance, but F maintained its performance. So still giving you, according to what was actually recorded from the re-engage, F would have been performing quite well. And in this, for this particular event, one could argue that the current configuration performed okay. This is where things take a turn. For the higher rainfall events in December, where 33.9 mm was recorded, we can see that F, the current configuration, let's start there, was nowhere near. So 48 hours ahead, you would have been receiving a forecast of maybe 70 mm. Whereas you can see that B and F did much better, right? Giving you around that 100 over 100 mm rainfall forecast. This is also why I wanted to make it interactive, because this is just visual. There's no precise value or better estimate. All you have is a rough estimate based on the contour. So you can't say maybe this area is about 140 or this next area is about 150. Right? You can't click and get the actual numerical values. So you're relying on the key, which is a range, and you don't know what that value is for that particular area. And again, it gets more interesting with this event from 2017. We can see that the current parameterization scheme is way off, and especially for the rainy season, or particularly for the rainy season. And so there's definite need to improve upon that. So let's focus on B and F. This one is 97.8, and so we would want to see, I guess, in the pink or blue region. F is quite fine in the pink or blue region, but when we look at B has a lot more brown around region 4, which tells us that the brown is closer from maybe about 150 to 200. And so F B, sorry, is kind of over forecasting. So we can argue that according to this research, F is probably the best scheme to use for Guyana, particularly during these high rainfall or uh, rainy season events. Now, in wrapping that up, a series of events were tested, 8 in total, and using this scheme of parameters that we call F, all 8 of those events were better forecasted 48 hours ahead of time than with the current parameterization scheme and size of the current WRF model. Right? So it's one thing to say that this is happening, and it's a next thing to prove that it is happening. And so there is a proof that we can improve. Now, I'm not going to say that the current scheme is totally wrong. It may be functional for the drier season, but definitely for the wet season, we need to fix it or change it or have some more analysis being done. But this is definitely a start. And so I just wanted to put this out there. With a bit of support, I think that this can go a lot farther and significantly improve local operations and flood mitigation. Right, so this was the initial tool. This is what it looked like during the thesis stage. Very static, so just images, PNG, JPEG images. As I said, you can't go and see anything by the hourly interval or sub-daily interval or even click on a particular location, but it still gave you a sense of over the next 48 hours this is what to expect. And so, as I said, my goal here is to really have this tool interactive, which is what I started by showing in the beginning. Different organizations can request different variables, and we can have that displayed quite nicely on the maps and select different locations that we might be interested in and see what is going on or what is likely to go on in those regions or that particular area.